In this final section of Chapter 1, we will develop one of the most important hyperreal functions. That's the standard part function. So we'll have to get some definitions here. But what the standard parts will allow us to do is when we're working our problem, we'll introduce hyperreal numbers to solve the problem. But once we're there, it's unnatural to work with hyperreals in the real world. So we'll need a means of stepping away out of the hyperreals into the reals again. And that's exactly what the standard part will do for us. So first off, let's start with the definition. And we'll talk about two hyperreal numbers, B and C. We'll say that they're infinitely close to each other if their difference is an infinitesimal. So if I've got two numbers and their difference is only an infinitesimal, then they're obviously very close to each other. So something just kind of, hopefully this is obvious, if I've got an infinitesimal and I add it to any hyperreal number, those two numbers are going to be infinitely close, right? Since b minus b plus epsilon, if I look at their difference, is just negative epsilon, which is an infinitesimal. If I've got a hyperreal number and it is an infinitesimal, it must be the case that it's infinitely close to zero, infinitesimally close or infinitely close to zero. And we can use this as another way of denoting numbers being a infinitesimal, saying that it's infinitely close to zero. And then finally, if both C and B are real numbers, so not hyperreal numbers, but the real numbers that you're used to working with, and they're infinitely close to each other, then they must be equal to each other, right? Because if they're real numbers and they're infinitely close to each other, that means their difference is an infinitesimal, and but their difference is also a real number. And because they're real numbers, their difference has to be a real number. And the only real infinitesimal is 0. So if they're infinitely close and they're real numbers, then their difference must be 0, which means that they're equal to each other. All right. So some theorems, a couple key theorems we'll look at. Theorem 1 says that if A and B and C are hyperreal numbers, then this squiggly line, our A, B, and C, saying that numbers are infinitely close to each other, it's gonna behave just like you're used to with equal signs. So if these are hyperreal numbers, then A is infinitely close to itself. If A is infinitely close to B, then B is infinitely close to A, and then the transitive part property. If A is infinitely close to B and B is infinitely close to C, then A is infinitely close to C. So theorem 1 says that this infinitely close symbol behaves quite similarly to our equality symbol. Some other things, so some other facts about the infinitely close. If A is infinitely close to B, then if A is an infinitesimal, then B must also be an infinitesimal. If A is finite, then so is B, and if A is infinite, so is B. Right? So this infinitely close preserves the categories that we talked about in the last section. So now we've got this idea of infinitely close, and here is the third and final principle that all of infinitesimal calculus is built on, and it's this standard part principle. So remember, we had the extension principle, the transfer principle. Those were talking about, hey, all the facts in algebra and statements that you know about with the real numbers, they transfer or extend up into the hyperreals. The standard part principle goes the other way. It says, okay, for every finite hyperreal number, so we're not talking about infinite numbers, but the finite hyperreal numbers, every finite hyperreal number is infinitely close to exactly one, and this is important, one and only one real number. So it doesn't matter what hyperreal number you have, as long as it's finite, then it's going to be infinitely close to a real number. And with that principle gives us the ability to define the standard part function. And the standard part function says, okay, well, let's take a finite hyperreal number. Since there's exactly one real number that it's close to, we'll just say this function, standard part of b, is exactly that real number. So we see that the standard part function, it's a function, and it's the first one so far that we've defined that starts in the hyperreals. There is no real version of this, but it takes the hyperreal numbers and sends it to the reals. So if b is a finite number, by the standard part principle, it has a real number that it's infinitely close to, and so the standard part function just sends it to that finite real number. And as I said at the top of the video, it's this function right here that we'll use to kind of extricate ourselves out of the hyperreals and have all our solutions have solid footing in the real numbers, which the real numbers are what we use to model the universe around us. So for the calculus to have application, we need to have it back existing in the reals. So that's why it's important to have this function. Since it's such an important function, let me list out the theorems for how to use it. And these are some very awesome features that if I want to know the standard part of negative a, well, I could just take the standard part of a and negate it. So we can see that negative signs kind of distribute out of the standard part. Also, standard part distributes across addition. So the standard part of the sum or difference of two numbers is again the sum or difference of their standard parts. It distributes across multiplication. Standard part of a times b is equal to the standard part of a times the standard part of b. Also across division, provided we don't end up dividing by 0. So it could be that b itself is a hyperreal number, or maybe an infinitesimal, so it isn't 0. But the minute I take its standard part, if it's an infinitesimal, I could have b divided by 0. So it's quite possible that a divided by b is defined a hyperreal number, but I can't use this rule if it turns out that the standard part of b is 0. The standard part, it has to exist because by the standard part principle, if a over b is a hyperreal number, a finite hyperreal number, then it has to have a real number infinitely close to it. It just you may not be able to use this part of the theorem. The fifth part of the theorem says that standard part distributes across exponents. So the standard part of a raised to the n is the same as standard part of a raised to the n. If a is positive, so we can take roots, then it also distributes across roots, and it preserves inequality. If a is less than or equal to b, then the standard part of a is less than or equal to the standard part of b. All right, so that's the background to the standard part. In the next video, we'll work some exercises to get used to using the standard part. And it's this theorem here, theorem 3, that really is at the heart of everything with our standard part function.